And now let's make our explosion a little bit more explosive. How we can do this? I go to my source and let's take a particles. Here we have our particles. And let's add the another attribute noise. So when we use the very old method, importing particles to our pyro simulation to get the extra influence, extra forces, in our case, extra divergence field. So what we're doing here, we set the 1D and let's create an attribute called div, like a divergence. This can be animated, we can apply the remap, and maybe it's like a 0 or like 0, I don't know, 0.1 maybe for minimum. And the push duration a little bit smaller to make it faster. The element size also 0.5, let's say. And yeah, well, we should have values lower than 0. Okay, so that's our divergence attribute. We can see the minimum is 0.1, the maximum is 0.999, so it's almost 1. Cool. And let's call this add div. Let's set a null object. Null object, let's call this out div. And let's copy this guy, copy the path. And inside of our dot network, what I want to do, I want to import those particles inside of our simulation to import our divergence div attribute into the divergence field. How we can do this? We can add the subsolver, which can help us to get those particles. Let's add a merge node, connect it to the last input, which is forces. It's not basically forces, but we can apply this element here. Inside of the subsolver, let's get div. Let's name it get div. Inside of the subsolver, we have different elements which we don't need to use. So simply object merge and paste our divergence particles. Okay, so that's our particles. We can see them. Even here we can see our particles. So we take our particles and put them inside of our dot network. So now what I want to do with those particles? Well, the first thing we can add a name for those particles. Let's say div particles. Let's set a name for those. And now let's put some information. So if you want to put some information to the field, like, I don't know, let me just look at, yeah, like here with our burn attribute, we create some kind of variable, we change something in this variable and then apply those values to the attribute. So the same stuff we can apply here. We will create a temporal field, put some information inside of this field, and then add this field to another one, to divergence in our case. So before we put some information, we need to create this field. Using the gas match field node, it's a simple node which can create a field using the reference field. So let's create a temp div field, we can call this, based on the density, because we use the scalar, we use the float information, so it's a scalar field. And we can say constant border type if you want to. Let's rename it create temp divergence field and connect it to the merge. All right, so now based on the density as a reference field, so we take the settings from the density and put inside of the temp div field. Now we need to take our particles, take our div attribute and rasterize this div attribute into the temp div field. How we can do this? Using the gas particle to field node. Okay, this our, all right. And I'm going to set temp div. So destination field is temp div, and the particles is our div particles. All right, and the attribute we want to use is our div attribute. Okay, that's this what we create here, div. Cool. I just want to make sure that I call it div. Paste it here, and what we can do also here, we can control the extrapolation cells. We can set the accumulated or not. So there's many different setups we can use here, but I'm gonna leave them by default. And now if I want to, so I take my particles, take the div attribute and put inside of my temp div field. Now I need to take this information and put inside of the divergence field. We can do this by a few ways. One of the most simpler is gas calculate node. Inside of this gas calculate node, we can use many different operations. We can calculations, copy, add, subtract, multiply, and all other stuff. So we have a destination field, which is divergence, and we have the source field, which is div. So also we have here a different setup for the destination processing, source processing, post processing, destination blend processing, and all the stuff. So I want to work with the source processing, and by default we have the source pre-mult, which is mean that we take all values from the source field is not a div, source field is temp div. Okay, you need to make sure that all is properly, and it copying the values. Let's set add, so I add values from the temporal div field into the divergence. Let's set 10 here on the source processing. And we have, boom, even big explosion. So let's compare it. Let's go from camera view. Now this explosion is much, much bigger. Ba-bam. So if we disconnect this thing, we can compare results with this explosion, yeah, and using our divergence custom field. Bam, that's much bigger. You can do it even more, like 15. So it's up to you how much you want to expand your explosion, how big it should be. All right, that's looking fine. The first explosion and now another explosion. Well, maybe it's too much. Maybe it's too much. Maybe you can go to source and decrease this diversion from the burn like to 1, and then here increase to like 25. Yeah, it's looking interesting. So you can change those parameters as you want. All right, so let's do another important thing here is that's gonna be my custom or particles. Come on, particles divergence. Okay. Let's add some color, some interesting color to this. Also, what I want to do, I prefer to use a very useful node which call gas vortex confinement node. It's a very powerful tool for creating more like vortices simulation. So what it's doing is boosting. Let's go to help. And it supplies force confined to the velocity field, the force which amplifies existing vortices with the intent of undoing the diffusion that occurs during the diffusion stage of the fluid solver. So the main thing, the main problem of many simulation, well, in fact, the main problem of CG simulation is that when we apply a divergence, like let me draw something. Let's imagine that this is our cells, this is our voxels, and we put some divergence in those voxels, like 1.5, etc., etc. In my FX Artist training, I explained how works the Pyro using the different equations like Navier-Stokes and all other things, how we create simulation, what is the divergence, what is a projection. So one of the simulation stages is create the non-divergent velocity field. So if you back to our PyroSolver, let's open it, allow editing of content. We can look at the stages we have inside of this solver. So if you look closely here, you have advection, sourcing, forces, and go down inside. Here a multi-solver, and where are those guys? Gas resize, reset divergence, advection. Yeah. So the first stage is the no, it's advection. It's not that. Where is the first advection? Reset divergence. Oh, here you have advection. Well, yeah. The first stage is velocity advections. So it's like a self-advection. Velocity advected by the velocity. Then we apply different forces. It can be buoyancy, it can be any force we apply. It can be multi-solver, which will add some information into velocity field. And this field became non-divergent because the divergence is begin to increase and became more than 0. So we have a projection stage. Where is our projection? It's a new solver, so I get in reflection. Somewhere is a projection, gas linear combination, gas advect. Oh, we have here pressure projection. So we have the gas project non-divergent multi-grid is the main node which actually create a projection. So the projection stage tries to move our information to create the non-divergence field. So if we have a divergence in this voxel, it will move information from this voxel to make a divergence 0. If we have a bigger divergence, the more information we go outside of this voxel, and it will create like a mushrooms. So that's why if you have a big velocities, if you have a big divergence setup, your explosion became like a big mushroom, because it tries to push information in all direction because of the divergence side of each voxel. Okay, so that's how it works the multi-grid. In older version of PyroSolver, there is a few different types of projection with a multi-grid, with a single projection, but for now they leave, I guess they leave just multi-grid. And also we have the gas repeat solver, which is actually tries to say how many types or how many passes we use for projection. So we can use this projection node 2 times, 3 times per one step. So we can set it here using the IOP interactions. Okay, so what I mean? I mean that with an explosions, with the high velocities volumes, we will have a very flat surface simulation. So because we lose our details, we lose our vortices. Like in real world, if you have a smoke, this smoke is not existing in the vacuum. It will move through the air. There is a different pressure, there is a different temperature, wind, turbulence, and our smoke will have a big amount of details till it disappears. In CG simulation, our smoke or any field with the projection stage, it will push information and it will, from time to time, it will lose the details. This information, this field became more blurry. All right, so to avoid such blurry thing, the vortex confinement can like create boost for those vortices to create a swirls on the surface. To it tries to catch more details in our simulation. It tries to, to boost all those things. So the gas vortex confinement, I prefer to use the settings between the 6 and 8, something like this. So an 8 should be fine at this moment. And also what I want to apply here is our turbulence. So we already have turbulence inside of the PyroSolver, but we can set up just one setting. So we can say, okay, we have a swirl size is 2.5, but what if I want to add very small swirls, like, I don't know, 0.1, 0.2, depending on your explosion scale or your simulation scale. So that's where we can take our gas turbulence node and apply it to this merge. Inside it, let's set the scale for my turbulence like 0.25. Okay, so the scale is very small scale for the turbulence, but let's increase the swirl size like to 20. So make it much bigger. Nothing more, just the big swirls with a small scale. All right, so let's call this a big scale. Big scale turbulence. Let's copy this, connect it to merge. Let's call this small scale. Small scale, cool. And with a small scale, I want to invert this thing. With a swirl size, I will make it like 1, but with the scale, I will make it bigger, like 7. Also increase the grain. Again, because I want to have more details. Also, we can use the control setting. You can see there's a lot of different tabs here, but mainly it's advanced using the OpenCL, different bindings, which field you want to use. You can use a density field. You can use, I know, the temperature field like a density field if you want to, for example. I don't know why, but you can do this. So in control settings, so let's control field by the density, like it here by default. But what I want to do, the minimum, again, I don't want to have less than 0.1. I don't want to apply this turbulence to a very low density areas because it will create a very noisy result. I didn't want to do this. So how many I add here? 0.1, 1.5. Let's do the same, 0.1 and maximum 1.5. Cool. And maybe increasing the fluence like 0.85, let's say. Let's back to my sim because we changed something. I want to look at the difference between the last simulation and the new one with the new turbulence setup. Well, it's looking not bad. It's looking not bad. Now, if you can see the nice show, I guess that I need to decrease a little bit of expansion. So now I can see the nice breaking shape for the explosion. So, and as I said, we also have the gas disturbance node. It's like a microsolver, which can help us to break this shape even more. But I prefer to use this gas disturbance node just on the high velocity areas. So if we have an areas which have a very big speed, movement speed, we need to break this shape using the gas disturbance. All right, so now how we can define which areas have a big speed? From one side, we can say, okay, let's set a control field and apply, I don't know, the velocity field like a control field, let's say, okay? But from the other side, how do you know how big velocities they have? Okay, from one side, in this case, in this case, what I want to do, I want to create again another one custom field where I put the speed for the velocity. So velocity is a vector, as you know. I hope you know. But I want to use the float value. So it's like control range between 0 and 1. How we can say the velocity is 1? It's the length of velocity vector. So somehow we need to find the length of the velocity and said, okay, if this length is bigger than, I don't know, 0.5, let's say, let's apply this disturbance to our velocity. Okay, so how we can find the speed of our simulation? Let's make another one thing here. Okay, so let's create a temporary field like we already did here with our divergence. So again, you remember the node we use for this? Right, gas match field. The gas match field, let's create, how we can call it? Val temp, velocity, temp. Let's copy this. So we create a new field, and now we use as reference field velocity, not the density, because we need to create the proper vector field. So let's connect it to another merge node. Okay, and let's connect it here. I want to put it on the first position because I want to calculate this information before I add this info inside of the gas turbulence node. Okay, the order sometimes is a very useful thing. Okay, so we create the velocity field. We create the velocity temporally field, and it should be a scalar field, in fact, because I will put the length of velocity. So how I can find the length of velocity? Using the very interesting node, gas analysis. So the gas analysis allows us to analyze many different information types. You can analyze the curvature, gradient, Laplacian, divergence, curl, normalize, and length. And that's exactly what we need. Calculate the length. So length of our velocity field, and we put this length into the val temp field. All right. So now val length. And that's how we now can use information. So basically with the simulation, if you go here in Paris, now you can see how many different fields we have. And one of those fields is our velocity temp. Also, we have a temp div field. If you want to, we can clear those fields. We can use some nodes just to put zeros after all those calculations. After each step, we can clear those fields if you want to. So now we can take this velocity temp and put this field over here. We can use it. Okay. All right. So now about visualization. Yes, field. Let's try to visualize this field. Let's try to do this. Let me turn off the emission scale. I don't know, can I use smoke? Can I use smoke or not? Unexpected parent data is vector field visualization. What? Why it's unexpected data? It's weird. No. should be like here. Oh, it's in gas analysis. Sorry. I connected the wrong node. Scalar field visualization. Use smoke. I want to use smoke, but it's as you can see a velocity field, and how I can remap it. Remap 20. Yeah, now you can see that I can visualize this velocity field, and I can look at the size of this velocity. Well, maybe use plane. Yeah, that's better. That's much better. We can use a plane. We can use the infrared, I guess. We can look at that. Let's disable the smoke also. So here we have a velocities, and it's our val temp field. That's what we look on. It's not a velocity field. If you want to look a velocity field, we can type here, press here, and that's our velocity. This is our val temp field. So now you can see that I changed the range. So if we look to range from 1 to 0, it's all red. So why I am using the scalar visualization? Because I want to look at the maximum of this field. If you type 20, you can see that there is not too many red regions. It's 30. Yeah, sounds like 30. Sounds like 30. So the thing is, now I can control the maximum and minimum range for applying this gas disturbance. So let's increase influence to like 100 and maybe 0.1 continuous. So now I can look at my field and say that I have not too many velocities with this scale of 30, and we can reduce to 0.1. Okay, so now you can see that in the beginning you can see those red values here. So we have a big velocities. I don't want to visualize those particles. Where is my, come on. I just disable visualizing because I don't want to see particles. And you can see that those red areas, 20, yeah, those red areas is areas where we have velocities bigger than 20. So maybe even more, like 25. So that's how we can control the how many disturbance we're gonna, let's set to 150, make it bigger. Okay, so now I turn off this guy. Let's back to smoke sparse, multi-field, emission scale 1. And let's look at my explosion again. It's bam. Again, maybe less divergence, 0.25. Yes, that's too much. I don't know, let's set 35. Let's set a projection to 3 iterations. So sometimes it's helpful because even without collisions, we can calculate how many times we use a projection. So you can see that which field we can correct: the density, temperature, and the flame field. And here are our explosions. So the next stage is basically adding collisions to explosions, because without collisions I can't create the final setup. I want to see how our geometry, what influence our geometry gonna have on our explosion. So let's go to our geometry. Let's me correct it here. Let's put it closer. Let's make it okay. I'm gonna move velocity, length. That's our project, and let's go to geometry.